Hi, my name is Qiao. I'm a PhD student at Northeastern University. Today I'm going to introduce our work in a 37-year Hindcast. This study provides Metocean responses along the US Atlantic coast, including wave height, wave period, storm surge, and etc. And this will serve as the foundation of our larger research scope to understand the offshore Metocean condition. This study is motivated by the offshore wind industry in US. Right now, wind energy is a hot research field and promising industry around the world. Wind energy does not produce carbon dioxide and is endless, which is a perfect solution for energy prices and global warming. From this average wind speed map, where dark color means higher wind speed, we can see that comparing to onshore wind, offshore wind area has the advantage of higher wind speed and closer to the big cities with large population. In this area with huge energy resource, currently we are only using a tiny fraction of it, which is the 5 wind turbines in Block Island, providing 30 megawatts capacity. However, a huge area along the east coast is now planning for offshore wind. In the wind vision study conducted by Department of Energy, the goal for US offshore wind is 22 gigawatts by 2030 and 86 gigawatts by 2050, which means we can reduce 0.2 gigatons of carbon dioxide emission per year. Then what is the challenge for offshore wind turbine design? In civil engineering, for example, we need to design the building to withstand a 300-year wind speed or a 1,000-year earthquake, and design code usually provides this type of wind map. Similarly, wind turbines are designed for a reference wind speed with 50-year return period. If the 50-year wind is high, then we need a stronger supporting structure, otherwise we can save the costs. But for offshore or area with hurricane risk, the designers need to figure out the 50-year value by themselves, which means we need to extend the wind map to cover the offshore area. Furthermore, offshore wind turbine needs to withstand not only wind, but also wave, storm surge, and other environmental loadings, which are usually correlated with each other. The concurrent Metocean measurements are very limited. And the goal of our research is to fill this gap by using numerical Metocean model to simulate sufficient Metocean data. Using both reanalysis wind field and synthetic hurricanes, with the Metocean data, we can advance our understanding in the joint Metocean condition, temporal characteristics, and we can also develop meta-models to expedite structural reliability analysis. However, before the Metocean model is applied to serve its purpose, it needs to be validated using historical measurement, and this is what I'm going to focus on during this presentation. This 37-year Metocean Hindcast help us to better understand the performance of the numerical model and provide a way to quantify the uncertainty in the simulation result. The outline of this presentation will be how we implement the Metocean model, how we conduct Hindcast validation, and what's the application of the Hindcast result. This is our model domain. It covers the entire US Atlantic coast. The mesh resolution is approximately linear towards water depths, around 20 km for deep water and 5 m for shallow water, and totaling of 66,000 elements. We have tested the result for various resolutions, and this setup balances accuracy and computational efficiency. The main driving force of the numerical model is the wind and the pressure fields. We use two modules from the commercial software Mike21 to simulate the Metocean responses. The hydrodynamic module predicts the surge, current, and etc., while the spectral wave module predicts wave-related variables, such as significant wave height, peak wave period, and etc. I will skip all the technical details on how to determine the parameters in each module and jump into how we conduct the Hindcast validation. In this Hindcast study, we used the wind and the pressure field from CFSR, which stands for Climate Forecast System Reanalysis. It's a global-scale reanalysis study conducted by National Center for Environmental Prediction starting from 1979 and is open to public. CFSR provides reanalysis with 6-hour interval and reforecast with 1-hour intervals. The spatial resolution for wind and pressure is 0.31 degree prior to 2011 and 0.21 degree afterwards. The wind and pressure field from 1979 to 2015 are taken as input to the McTurner model. We conducted a detailed validation, but due to the time limitation, I will only present the result from 5 buoys that validate the wave prediction and also 3 water level stations that validate surge prediction. These measurement locations are selected to cover as large areas as possible and also to provide measurement for a sufficient long period. From the bottom right plot, we can see that the buoys provide at least 10 years of concurrent wind and wave measurement, which will be useful to figure out whether the error in the wave Hindcast is induced by a numerical model or wind input. And all the 3 water level stations cover the entire 37 years. So, with the hourly measurement and Hindcast shown as the blue curve and the red dot here, how do we assess the model performance? We break it down into 4 aspects. The first is bias of monthly mean. It's important to know that the real measurement data might include errors, and some of them are not easy to be detected during the data cleaning process. The bias of monthly mean can help us to locate the overall large errors and to diagnose whether we're missing anything in the simulation or something is wrong with the measurement. The second is distribution of the hourly data. This is important to structure fatigue analysis. And for long-term conditions such as a 50-year wind and wave, we need to check the distribution of the annual maxima, and this is related to structure ultimate strength analysis. For distribution, we use quanta plot to examine whether the Hindcast and the measurement follow the same distribution. If so, it should appear as a straight line with union slope. And finally, we use Taylor diagram to assess the comprehensive performance. Taylor diagram is widely used in atmospheric science field, and we find it quite handy for Metocean field. In an example shown in the lower left plot, the angle of the radius represents correlation coefficient, distance to the origin represents standard deviation, and distance to the reference point represents centered root mean square error. Apparently, the closer to the reference point, the better the model performs. These are the monthly mean bias results for wind, wave, and surge. Different column stands for different measurement locations. For wind and wave, the prediction is in general unbiased, yet we notice 2 spikes in wind and 1 spike in wave. For wind, the error comes from measurement, and for the spike in wave, we found that several peaks in the measurement, which are probably induced by intense storms, are not simulated in the Hindcast. Unfortunately, the simultaneous wind measurements are missing, so we are not able to determine whether the error comes from Metocean model or from the CFSR wind input. For surge, there is a clear trend in simulation error. This is because we didn't include the change in mean sea level during the simulation, and is corrected for the following validation. The rest of validation results are shown here, where the blue is for wind, red is for wave, and green is for surge. In order to be compact and to be shown in the same scale, all the results are normalized. For the hourly and annual maxima distribution, where horizontal axes are the measurements and the vertical axis are simulations, we first notice some outliers. For buoy 41025, this data is recorded during Hurricane Isabel in 2003, and most likely something is wrong with the buoy, as the wave measurement increased suddenly and then stopped working. For the first water level station, the outlier data is recorded during Hurricane Hugo in 1989. Here we can see the measurement can be unreliable, especially during hurricane events. Disregarding the outliers, the quanta plot show a good match between the simulation and prediction. except for buoy 44009, where extreme wave seems to be underestimated, and if we are to use simulation data around that area, we will need some calibration. The Taylor diagram here shows the behavior of the annual data. We can see all the three variables we're looking at are quite consistent, with correlation coefficient around 0.9 and the center root mean square error of around 0.5. Depending on the specific application, the validation result can be used differently, and for the simulation uncertainty at location other than the measurement location, further efforts would be required. Lastly, I would like to present some application of this Hindcast study. The most straightforward application would be to create a 50-year wind and wave map for design purpose. Here we're excluding hurricanes because hurricane event might follow different long-term distribution and therefore is usually handled separately. Also, we're extrapolating the 50-year wind and wave independently, not taking the correlation into account. In the insets of both plots show the gumball extrapolation from annual maxima, where horizontal axes are wind and wave respectively, and the vertical axes are reduced variance defined by the gumball chart. On the left plot, we can see that 50-year wind is in generally higher at north, which is because the more frequent winter storm. And there is also a hotspot near South Carolina, which might be affected by hurricanes, as we are using a relatively simple criteria to filter out hurricane wind. On the right map, the 50-year wave basically follows the same trend. The propagation of wave is affected by not only wind speed, but also water depth and fetch length, so the location of hotspot will not match maximum wind speed. The Hindcast results are also used in the following research, and they are not presented here. Thank you very much for your time, and I would like to have further discussion if you have any questions.